Good afternoon, everyone. Thank you for coming here and welcome to my PhD defense ceremony. Thank you for being here, choosing to come here in this lovely weather outside. So first of all, I would give a little bit of background of my PhD thesis, which I worked in the past 4 years. So it was about understanding the salt crystallization in the presence of additives called surfactants. So first of all, we encounter crystals in daily life in various forms, like, for example, the pharmaceuticals, the medicine which we take. The food, for example, the ice creams or any other kind of food, so they also have lots of crystals. And the everyday electronics which we use. So they are composed of lots of semiconductor crystalline substances. And of course, we use them sometimes for, to do some convincing. So in all these applications, we need crystals in certain forms, certain shapes, and in certain crystalline form, in certain crystallographic form. So in order to achieve that, so we first need to understand crystallization in the presence of different additives and different environments. So first of all, for that we need to understand what crystals are. So crystals are, they are a form of solid state in which the composing atoms, ions, or molecules, they are arranged in an ordered fashion, and they have a long-range order. So this, the crystallization happens when we have molecules, the composing moieties, which combine together by the process of evaporation or cooling to form crystal nucleus. This crystal nucleus later grows into full crystal. So in order to control these shapes and sizes and the crystallographic form of these crystals, we need to go to do crystallization control. So this crystallization control, it's done in two ways. So one is by adding the chemical additives. So in this case, in my thesis, I have used surfactants. So surfactants are these special kind of compounds which have a hydrophilic head, which means they can dissolve in water. And they have a hydrophobic tail, which means they can dissolve in oil also. So this kind of composition gives them a unique property of adsorbing at the interfaces, which means that they can dissolve two different phases. So this kind of property makes surfactants ideal for using as cleaning agents. The second parameter which can be used to control the crystallization is physical environments, to change the physical environments. In this thesis, I have used confinements. So the confinements in the form of thin films, in the form of microcapillaries, and real porous stones. So first of all, I will introduce you to the confinement in thin films, for which we take the real example of this is the salt creping. So you might have seen these buildings, particularly in the brick buildings in Amsterdam, which have this white layer of salt on top of it. So this is basically the salt which is present in the soil, gets absorbed into in the bricks, and then with the help of salt creping, it spreads all over. Another kind of place where it is seen is in agricultural soils, where a salt-contaminated soil leads to the contamination of the surrounding area by letting the salt to creep around. So in order to understand its basic phenomena and how possibly we can control it, we made a setup in the lab in which we could reproduce this experiment. So this setup is composed of a solid substrate, which we bring in contact with the salt solution, and then we let the solution to evaporate, and in the meantime, we monitor it. So this is how it looks like. So here what you're seeing, it's a salt solution kept in a petri dish, and then we bring into contact a cylindrical glass slide. And we let it evaporate at a very low relative humidity. So what's happening with time is that the crystals are forming in the bulk, and at some point we see that the crystals grow on the solid vertical substrate. So this is salt creping done in the lab. And then in order to see, is it working there? No? Okay, it's working here. Okay, so I think you would have to believe me. So you can see the pictures in the thesis in chapter 5. So in the other case, we have the same experiment. So this time, we added some okay, now the whole presentation is good. We added some additives called CTAB. So it's a surfactant which actually promotes the crystallization. So here we see that, well, I hope, I wish we could see that. I can see that, but so the crystallization happens much faster and it extends much further on this glass rod. Actually, completely stuck. Yeah, so
it's completely stuck.
The projector is stuck, the computer is working.
It should be click there from the link.
The projector is not showing anything. It's working here. So yeah, so there's some technical fault with the projector because everything is working here fine. It's not taking the signal there. So, yeah. Let's see if it works. Yeah, so here, yeah, we get it back. So what I was saying earlier, so the salt actually grows on the solid substrate, and it goes to quite a few centimeters. And when we add CTAB, so what happens differently, I would fast forward it this time. So it goes much further, and it walks much further, much faster. And in the end, we form this kind of Christmas tree-like structure. And then in the end, we added a different kind of surfactant, and there we see that no creeping took place. So here we can clearly see that one surfactant improves the creeping phenomena and another inhibits it. So in order to understand it, so we took a close-in zoom picture, so there we could see how these films are actually formed. So from looking at this data, so we finally came up with the mechanism of creeping in which the salt crystals are formed at the meniscus, as you can see in the picture. And then when the evaporation happens, so this gap between the liquid film and the glass cylinder decreases, and it leads to formation of this film, which ultimately drags the solution on the smooth glass surface. And in the end, we form this creeping-like, the network-like structure, which is responsible for spreading the salt everywhere. So the next experiments about confinement which we did were microcapillaries, so in which we do similar experiments. We load the microcapillary with a salt solution and then let it evaporate. And at some point, we see that the crystals form at the interface in a very fast way, in a very quick speed. So there also, when we add a different surfactant, we see that there is some difference in a sense that it forms the crystals in the middle, and these crystals grow much faster. So in order to explain that, we see the variation of volume with time. So in normal salt, it would crystallize at the saturation of 1. However, when we had these solutions in microcapillary, so this crystallization was prolonged much more, and we could see that the crystallization happens at the solubility of almost 2 I. And when we were adding surfactants, this process was slowed down even further. So in order to explain this, we proposed this scenario that the salt crystal normally, as we saw in the first movie, forms at the liquid surface. And when we have surfactants present there, so this surface is unavailable for the crystallization to take place. And same happens with the glass surface also. So what happens is that the second step, the nucleation process is inhibited, which leads to the inhibition of crystallization because of surfactants. So in final, so what we concluded, the main conclusion of the thesis were like salts, when we crystallize salts in a confined media, they crystallize in a different way. And different salts, different surfactants have different influence on the dynamic of salt crystallization. And the surfactant chemistry can be used to control the crystallization process in a desired way. Thank you for your attention. Yeah, I think this guy would come.
You have also this one, the formula.
I have the same thing, yeah, I bought it.
Sorry?
I had it.
Oh.
I take it from you.
Ladies and gentlemen, welcome to this special meeting of the Doctorate Board of the University of Amsterdam on the occasion of the PhD defense of Mr. Qazi. Dear candidate, to open the discussion, Please read out aloud the first part of the formula.
By authority of the Rector Magnificus and the Doctorate Board of this university, I shall, during this hour, in order to obtain the doctorate, publicly defend my thesis entitled Influence of Surfactants on Salt Crystallization. I entreat all those who wish to voice criticism of the contents of this thesis to do so in a truthful and lucid manner, so as to provide an opportunity for an ordered exchange of views.
It is a pleasure to welcome in particular guests from outside of the University of Amsterdam. In particular, Professor Prat from the Institut de Matières Fluides à Toulouse, Professor Bain from the University of Durham, and Professor Dietze from the University of Oslo. The opposition will be started by Professor Prat.
Dear candidate, first of all, I would like to thank you for your work, because I enjoyed very much your work and the variety of system you look at during this PhD. But perhaps you know that for some reason I cannot explain, I like very much porous media. And so I will have some discussion with you on the last chapter of your thesis. So maybe you can look at the figure 6.5 on page 146. And I would like to discuss whether or not you have the solution in contact with your crust when there is this change in the evaporation rate. Okay? If we look at this figure, we see that when the ratio between M and M0 is around 0.4, you have this change in the evaporation rate in the presence of salt, okay, in a surfactant. And so what I would like to know is whether there are solutions in the porous medium in contact with the crust or not.
Highly esteemed opponent, thank you for your kind words and interesting question. So if you begin the drying process here, so the capillarity brings the salt solution to the surface in the beginning, and then when the salt crust is formed, so the only thing which changes at that moment is that it cannot directly evaporate into the surface, into the atmosphere. So I can speculate there. So we didn't really look inside what's happening under the crust. So I can speculate that the the capillary suction of water brings water to the undersurface of the crust. So do you mean what is at the top of the crust?
No. The first question is very simple. Do you think is there water in the porous medium in contact with the bottom of the crust or not?
In the bottom. So I think, when we measure this, when we take out the samples at the end, we don't see any crystallization at the bottom of the crust. So, which means all the water, it's being driven, so the driving force for the water to come from the bulk of the stone to the top of the surface is basically the evaporation. So the evaporation is taking place only from the top and from the sides. So in the bottom of the stone sample, there is no evaporation taking place. So I don't think there would be any salt in contact with the.
No, actually, what I wanted to discuss is the fact that, based on the high level, high mass, when the change in the slope occurs, you should have water solution in contact with the bottom of the crust. Okay?
Mm-hmm.
Do you agree?
Yeah, so I can see that it's still homogeneous. So the saturation of the stone is still homogeneous. So then, of course, it would be in the same way as it was in the beginning. So it means there would be some salt solution in the crust.
The next step is you argue that in the crust there is only gas diffusion. We are in a period where the ocean rate is. So we are in a situation where we have diffusions in the crust with
Um,
What, in other words, why solution rising into the crust?
So solution, what we explain here, the slowing down of evaporation process is, so it's because the crust is just creating a barrier for evaporation. So
I don't understand if the crust is a barrier, anyway you assume that this is a porous barrier.
to some extent,
You have
yeah.
some vapor flow through the and what I don't understand is if this crust is porous and in contact with the solution, why? Possible. The solution is wetting, but there is no liquid in the crust according to your assessment.
So you mean if the liquid is in contact with the porous structure of the crust, why it's not directly coming to the surface rather than diffusing? So that could be one of the interpretation of this data. But however, when we in the further pages, when we exactly in the second picture, so we see that this evaporation rate in this regime, so we just following the first regime is exponential. So that is well explained by the diffusive transport. So if the earlier case was true, then we would still see to some extent some sort of linearity there also. So the rate would be slower, but it could still be linear. So, and also in this diffusive regime, we have a square root of time dependence.
So if you have a square root of time dependence, then your evaporation rate varies at the inverse of the square root.
Mm-hmm.
So this means that the evaporation rate is decreasing. How do you explain the fact that the evaporation rate is decreasing?
So if you look at this at the equation where we see the in page 151, so there we are calculating the rate of decrease by taking into consideration the diffusion through the crust, and there we have used the thickness of the crust. And as the crystallization continues at the top of the surface of stone, the thickness of the crust also increases. So the L in equation 6.6, it also increases with time. So I would say this is because of the increase in the thickness of crust, which continues to make the evaporation rate go slower.
The crust is growing downward in the direction inside the post medium. There is no liquid in the crust. So if the thickness changes, the crust is growing inside the post medium.
So there is some sort of, if you look at the pictures of the opened up stone, so we do see some crystallization at the immediate subsurface of the stone. So there is some sort of growth which is going inwards.
Then did you try to determine the, for instance, effective coefficient data? Because page 1 of your equation, you end up with some scaling and square root. Try to determine effective coefficient or the thickness of the crust.
So as far as calculating the diffusion coefficient is concerned, we use the existing model, which has been, I think, which has been used in the other studies also, and so our data was corresponding very well with it, with the diffusion coefficient which we were calculating by using the normal thickness of the crust. So we did not go further to calculate the effective diffusion. Yeah.
Then if we look at the well, at the red curve, we see that for at the very end of the experiment, there is some change in the slope. Okay? The trend is not anymore the
Yep.
on the right.
Mm-hmm.
How do you explain this change?
So if you look at it, the saturation at that moment, where we see the change in the rate, it's around 2% or around. So it's barely some water left in it. So I don't see any hydrodynamic reason there to change the rate.
Okay, because so suppose that we because what we can maybe discuss a different theory, which we can assume that the crust is wet. Then question is the density of pores at the surface. Since you have images of the crust surface, you try to estimate this density of pores, so the number of pores per centimeter.
We did measure the pore size, but not the pore density, because I think it was one of the reasons was that we were convinced with the explanation of the diffusion through the crust. So I think we didn't explore the other possibility which you are suggesting, the wet crust. So in that case, that could have been a reasonable thing to do.
There are relationship between the evaporation rate and the density of the surface. If we apply, use this relationship, then we can also find behavior wet crust. Suppose that this density of pores the surface change because of
Some clogging along the drying process. So I am not sure that we can say from the scaling law, the fact that you have the square root of time, that the crust is dry and this is controlled by diffusion within the crust.
Yeah, so I agree.
What you show is there is a square root of time behavior. That's fine. But
I agree. This is still open to debate in the literature, and people. I think that would be the future outlook to look at it, to look at the alternative explanation.
I propose we go to the next opponent. Thank you very much for your. The next opponent is Professor Bain. Please go ahead.
So, dear candidate, first I'd like to compliment you on the lucidity of the explication of your thesis. It's a very interesting piece of work and I've enjoyed reading it. I've been interested in surfactants and surfaces for 30 years, and for perhaps 5 years or so I've been interested in evaporation, so your thesis brings together two topics close to my heart. It's also an area where we've been doing some work ourselves recently, looking at evaporation of solutes in very small droplets, so picoliter droplets. So I'd like to start off by talking about this, if you like, the condition where you see crystallization of your sodium chloride solutions. As you're probably aware, I mean, you've related your thesis to the problem of salt formation in buildings and in soils, but it's also very important in atmospheric chemistry, in aerosols. And there's been quite a lot of work in the aerosol community looking at the crystallization point of sodium chloride solutions. And I refer you perhaps to a recent paper from Jonathan Reed's group that was published in 2018 using an electrodynamic balance. And one of the things they found was that the crystallization occurred extremely reproducibly at a supersaturation of 2.04 at the surface, which is significantly higher than the values that you see. And they measure an efflorescence relative humidity of about 45%, which is significantly lower than the humidity that you're carrying out in your capillary experiments. And in our own experiments with very small droplets, we find that above about 45% relative humidity, we occasionally get rapid nucleation, But if we don't get rapid nucleation, we don't see any nucleation at all. So at 55%, for example, we would not see any crystallization, although admittedly we do not run experiments for hours, we only run them for minutes. So I just want to, in the light of that information, if you could talk a little bit about what you think are the mechanisms underlying crystallization, so homogeneous versus heterogeneous, interfacial versus bulk.
Highly esteemed opponent, thank you for your kind words and interesting question. So indeed, as you mentioned, in case of droplets, the volumes, I assume, are from the Jonathan Reed's group, so they're pretty small. So in the chapter about crystallization in microcapillaries, so we have the similar results. So in a microcapillary, in a crystallization taking place in a microcapillary of 100 micron diameter, we do see that in case of pure sodium chloride, we already see the supersaturation of around 1.5 in chapter 5. Yeah. And when we add surfactants there, so we see that if you look at the picture 5.2, so when we add surfactants, so it goes even higher. The maximum which we could reach in the presence of additives was around 1.72. So I agree with that. So the explanation for that has been provided in the article preceding to my thesis, was that when we have these very small volumes, the probability of nucleation also decreases. The probability of heterogeneous sites for nucleation also, in the presence of heterogeneous nucleation sites, also decreases. So that's one of the explanations for why nucleation gets so much delayed. And I think your second question was about evaporation?
Well, about the efflorescence relative humidity.
About the relative humidity?
Yeah, in the sense that at 55% relative humidity, the atmospheric experiments would not see any crystallization at all, whereas you seem to be seeing it in your systems. So
I think the reason there is that at 55% relative, if the liquid solution, it's highly supersaturated. Let's say, for example, sodium chloride, if it reaches to a supersaturation of 1.9, the equilibrium water vapor pressure above the sodium sulfate is already to the level of, I think, 55%. So there is no evaporation anymore. So we had this similar problem. If you see again at the same graph, the evaporation rate becomes very slow. So that's because the difference between the equilibrium vapor pressure above the solution and the atmosphere decreases. So if our supersaturation goes high enough that it coincides with exactly the same amount of water vapors in the atmosphere, then the evaporation would stop. So I guess the reason there is the solution is becoming highly supersaturated. So if there is a little perturbation put in, I think crystallization would happen.
Thank you. If I may ask a second question, Mr. Candidate, which is unrelated to the first question. So the second question concerns the mechanism of creeping. So you argue fairly convincingly in your thesis that the difference between your two surfactants, between the tween and the C-tab, you associate that with a contact angle, and you relate this to capillary length in your argument for why some crystals will sink and some systems will tend to creep. Now, the creeping phenomenon is not limited to large-scale systems, nor is it limited to ones where gravity is acting. So, for example, in previous work from the Shahid group, there have been measurements on sessile droplets, and you can reduce the size of those sessile droplets down to the picoliter scale, and one still sees creeping of some salts, but not other salts. So I wonder if you can say a little bit more about what you think is the mechanism by which the liquid extends beyond the boundary of the droplet, and why it is that new crystallized form, given that you need supersaturation, rather than simply the existing crystals growing bigger, which will happen at a supersaturation of 1.
Highly esteemed opponent, thank you for the interesting question. So in our case, as we are hanging the substrate vertically, so gravity comes into play, which doesn't allow the creeping to happen. So your question is like in the droplets, so when crystal forms, so there is a capillary suction which actually pulls the newly formed crystal inside and brings it to the bottom, to the center. So it gives it a kind of anti-coffee stain effect, if you will. So in case of surfactant, what it's changing basically is In the same chapter, we first do some bulk experiments to see the individual influence of surfactants. If you see the figure 4.5, we see the surfactants, different surfactants having different influence on the nucleation. So when we have CTAB, it leads to the formation of multiple nuclei, and when we have tween 80 present, it inhibits the formation of multiple nuclei. It forms only one nucleus. And how it plays into the creeping phenomena is that if we go to the illustration 4.13, so here the second step, which is necessary for creeping, is the multiple nucleation. Even if we have reached to this critical contact angle and we don't have multiple nucleation taking place, we would not see creeping. So there are two things here which support our assumption here, is that we don't see the creeping when we have the additives which inhibit the formation of multiple nuclei. And the second thing is when we have high relative humidity. So when we have high relative humidity, the same crystal gets enough time to grow bigger, and then it falls into the solution. However, when we have very dry environment, the liquid film dries quite fast, and then it allows the formation of a second nucleus on the top of earlier one, and this goes on further to form the network which ultimately serves as a medium to transport the liquid from reservoir into the far off distances.
So if I just follow that up a little bit, though, I mean, if you have a crystal there already, it will grow to supersaturation of 1, whereas to nucleate a new crystal requires a higher supersaturation than 1. So how do you generate the higher supersaturations required for the secondary nucleation?
Highly esteemed opponent, thank you for the interesting question. So in this case, in the case where creeping is happening, I would focus only on that one. So there, the creeping, for the second nucleation, it's taking place only from a film, and the environment around it is really dry. So I think the time needed to create supersaturation at that moment is very low. So we are seeing highly supersaturated thin solution film on the top of existing crystal, which is later favoring the creeping phenomena.
Thank you. So may I ask us one final brief question, which refers to the...
Very short.
Very short. So is it possible that Marangoni effects are taking place here, and that the film is spreading out due to surface tension gradients caused by the effect of the salt concentration on the surface tension, and therefore the influence of the surfactant on the air-liquid surface tension is what is giving rise to the different behavior?
Highly esteemed opponent, thank you for the interesting question. Indeed, so there could be Marangoni effects playing a role, but then if we see the role of two different surfactants, so CTAB and tween 80, so both of these surfactants decrease the surface tension. So I would think that in terms of Marangoni flows, Marangoni effects, so both of these surfactants would have the same consequence, but we see that they have different consequence in terms of creeping. So I think there would definitely be Marangoni flows, but they are not significant enough to create to enhance or to inhibit the creeping process.
Thank you.
Thank you for your position, and I give the word to Professor Gieste.
Thank you very much, Rector. Dear candidates, thank you for letting me serve in this committee, and it's been a very interesting thesis to read. I've learned a lot from it, and I think I'll use this occasion to ask you some questions in order to learn something more. And maybe I'll be a little bit off tangent, but you had some experiments where you saw incorporation of one type of surfactant into your crystals, but not the other molecules. It was a very nice method. Normally, people have to go to a large instrument like a synchrotron radiation facility in order to see the changes in crystal structure, in order to see incorporation, whereas you just dissolved it again. So my first just technical question on that is, you say you washed the crystals, and is it enough just to rinse it a little bit and you're sure that you're rid of everything that's on the surface?
Highly esteemed opponent, thank you for your kind words and an interesting question. So what we do basically when we isolate the crystals grown in different surfactant solutions, so we put them in a saturated salt solution and we leave them there for some time. So since both of these surfactants, they have quite high solubility in water, so we think that it's pretty enough to rinse off any surfactant molecule which might be attached to the surface. And if it would not be, then we could also, and also we see a specific incorporation. So we see in case of 280, we see a significant change. And in case of CTAB, we don't see any change. And also given the size of the crystal, I think the amount of surfactant which would attach to the surface would be very infinitesimally small. So that could not have as such a big influence on surface tension as we see in our case in the graph.
Okay, thank you. If I may follow up on the same topic. So you have some explanation of why one of the surfactants got incorporated and not the other. And you said that it's probably due to the negatively charged sodium chloride surface, and that one of the cationic surfactant got repulsed from this. How do you determine the charge of the surface of sodium chloride?
Highly esteemed opponent, thank you for the interesting question. So we had a method of measuring the charge on the surfaces, which I have shown in chapter 3. So which we used for glass beads. Mm-hmm. So we did the same thing for the salt also, so we could measure this the absorbance. And secondly, also we also take this from the literature. So in literature, it's pretty much demonstrated many times that the charge on this crystal, sodium chloride crystal, is negative.
But so does this not depend on which surfaces they are? Because some surfaces are terminated plus minus, so they're neutral, and others are terminated differently.
So that's one of the good things to work with sodium chloride. It mostly crystallizes with 100. So in most of the cases, it has the same surface. Mm-hmm. So that was one of the reasons to do a lot of studies on sodium chloride for this thesis.
And how is the 100 surface terminated?
If you want to terminate, is that question?
What does this surface look like? Does it have only chloride on top? Does it have only sodium on top? Does it have sodium and chloride in equal amounts?
That's in the first chapter, figure 1.1. Mm-hmm. So 100 of sodium chloride is it's stoichiometrically sodium chloride are present in a 1-to-1 ratio.
Yes. And so what is then the origin of the surface charge? If it's terminated neutrally, what is the origin of this negative surface charge of the sodium chloride?
So I'm not really sure where would the charge come from, but I think it would depend upon the charge density of the ions also. Mm-hmm. So if there is a difference in the charge densities, there might be some residual negative charge left on the surface.
Okay, because the reason I'm interested in this is, as you pointed to in your thesis, that calcite, or it might be interesting for understanding biomineralization. And there have been lots and lots of studies on incorporation of organic molecules in calcite, for example. So I was wondering how, and you say that your result brings some new insights that I can use. So how can I use this insight you've got to understand more about incorporation in calcite?
So the insight which I would say can be gained from this work would be to focus on, to predetermine the interaction between the additives which you want to incorporate into the crystal and the crystal surfaces. So that could be used, there could be some computational tools used to do that, to estimate the affinity of certain, in case of biomineralization, to measure the affinity of proteins with the crystal. And another thing is, like, I think that would not be the case with macromolecules or with surfactants, would be to see how well these molecules can fit into the existing crystal structure.
Mm-hmm. But directly from your results, I would need to know something about the charge of calcite in order to predict which surfactants would affect it or not?
So one thing would be that, and another thing which we stress, which I stressed in this thesis, was about the role of confinements. So the role of confinements, in a sense that when the crystallization happens in a confined media, so we most of the times see very high supersaturation, and at a very high supersaturation, the rate of crystallization is different, and the crystal form in a different way. So that could be one of the determining factor leading to the incorporation of proteins or incorporation of any macromolecules into the bigger crystal structure.
Okay, thank you very much.
Thank you for your position. Your position will be continued by Dr. Noorduin, who is also a guest at the University of Amsterdam today from the Vom Institute Amhof. Please go ahead.
Thank you very much, Mr. Rector. Dear candidate, first of all, I would like to congratulate you with this very nice thesis that you delivered. I read it with a lot of pleasure, and I'm really amazed that even simple systems like kitchen salt can still amaze us in such a way, and therefore I also have some questions, of course. And so first of all, I would like to go back to page 122. So we already briefly discussed a little bit the nucleation of sodium chlorate in this capillary, but I was wondering when I was looking at figure 5.2, how do you actually measure here the supersaturation that you calculate on the y-axis?
Highly esteemed opponent, thank you for your kind words and interesting question. So we measure we basically measure the concentration. So when we load the capillary with a salt solution, so we take the initial volume, we just measure it, we know the diameter of the capillary, and then from image analysis we calculate the concentration. And then with time, when the solution dries up, the length of the column changes. So according to that length, the diameter is constant, we get the volume, and from that volume we calculate the concentration. So that's and then using that, we can calculate the supersaturation in this case.
Thank you very much for this explanation. So I'm wondering then, we also just learned that for instance, the tween, this also gets incorporated into the crystal structure. And so in your calculation of the supersaturation, you basically, I guess, assume that the saturation concentration remains constant. Or do you take some measurements into account for this for each additive that you use?
Highly esteemed opponent, thank you for the interesting question. So we measure the concentration of only salt during the process of evaporation. So if I understand your question correctly, is that you say if the concentration of surfactant is changing, or? Well,
what I mean is that if you're crystallizing, if you measure the saturation concentration, this is basically the moment that if you add more, you will see growth. If you have less concentration, you will dissolve the crystal. If you add the surfactant, this can well, it can change the kinetics, of course, but also thermodynamically the solubility. And especially since tween is incorporated into the crystal, I can imagine that basically, the ternary phase diagram changes.
Highly esteemed opponent, thank you for the interesting question. Actually, so we did some preliminary experiments to see if the concentration, if the solubility of salt changes in the presence of any surfactant. So one thing is that we did not measure, we did not find any change in the solubility. And the second thing is that the concentration of surfactant which we are using is very, very low. So it's of the order of millimoles. Okay. So at that time, at that concentration, I think it's too low to make any change in solubility.
Okay, I see your point. So then, if I move to page 123, so next to it, I read that both the CTAP and the tween that you both use as surfactants, or that they both inhibit the nucleation. But then I just finished the chapter before, so chapter 4, and in the conclusion part, you say that, let me see where this is exactly. Sorry, on page 108 at the bottom, you say that CTAP in these experiments promotes the nucleation.
So, highly esteemed opponent, thank you for the interesting question. So there is indeed a difference, but the difference, we also have two different systems. So one is microcapillary, in which, and it is a microcapillary, so it's a confined system. And another thing is that the experiments in microcapillary are performed at very high relative humidity. So it's at the relative humidity of 60%. And in case of creeping, the experiments are performed at the relative humidity of 6%. And another thing which we mention in creeping is basically it's not if it's prolonging the nucleation or decreasing the nucleation, but we are saying it's making it possible to make more nuclei at the same time. So here we could probably it happens same in the microcapillary also, but the saturation at which the crystallization begins is so high that there is not much. The crystal grows so fast that it consumes all the supersaturation around it. So there is not much salt left to form a new nucleus.
Okay, Mr. Rector, is there time for one very short question? Okay, thank you.
Position is continued by Professor Bolhuis.
Dear candidate, I also want to congratulate you with your very nice thesis, and I dive straight into the questions from here. So in chapter 1 on page 12, you introduce the surface excess concentration, and you measure this by taking the surface tension and determine the slope as a function of surfactant concentration. Now in chapter 3, which I want to go to on page 56, you present these curves. However, even in a linear log plot, they don't look straight. So you do have a linear regime close to the CMC, but before that you don't. Can you explain this to me?
Highly esteemed opponent, thank you for your kind words and an interesting question. So we have in this we have a plateau after CMC, and then we have a straight we have a linear straight line, and then we have we take the slope from the straight part of it to calculate the surface excess. So
that's correct. Mm-hmm. But what happens if you go to lower concentration? Why do you see the bending of this curve? Can you also interpret that in terms of surface excess concentration?
I think you mean why the surface excess is decreasing in case of when we have higher salt concentration. So that we explain in the same chapter. It's basically we don't have there's not decrease in surface excess per se, but it is more that in the presence of high salt concentrations, the surfactants form ion pairs. So when we have pure ionic surfactant, So in the Gibbs adsorption isotherm, we use the N, the dissociation, we take into account, but when we have salt present, based on the SFG measurements also, we don't divide it by 2. So
Okay, that explains the difference in figure 3.5, but it doesn't explain the flat curve at very dilute surfactant concentrations.
Highly esteemed opponent, thank you for the interesting question. So I think you mean why it's reaching to plateau again when the concentration is very low.
Yes.
So that could be, the reason could be this, at this concentration where you see the very low concentration, the very small change in surface tension is already in the concentration of micromoles. So the concentration is not high enough to change the surface tension.
So you say the partition between the bulk and the surface is just not at
Is not enough.
Not enough. Okay, that's a fairly reasonable explanation. Let me then go to page 56, where you state that adding the salt lowers the CMC, and you actually also measured it, of course, and you explain that by the fact that salt screens the electrostatic interactions, and this seems very reasonable. But have you also considered a different explanation, namely that you could actually change the chemical potential of the solute in the electrolyte solution? This could be increased, which also would have the same effect.
Yes, so that could be an additional explanation for the decrease in the CMC. But I think that would be more, we could add that more if we could do some quantitative treatment on measure the chemical potential for that. So we did not have enough time to supplement the explanation with the alternative explanation.
Well, on page 71, you do show an effect of the electrostatics, and that's that the radius of the hydration radius in figure 3.7 that changes as a function of salt concentration. And that is, of course, because of the electrostatic screening. But can you explain what's happening here? Because I see an increase of a factor of 2 in radius, which actually translates into a factor of 8 in volume if you assume spherical micelles. So can you explain that?
Highly esteemed opponent.
Short answer in view of the time.
Thank you for the interesting question. So what we say here is that the size of the micelles is increasing because of the change in the change in screening. So because of the screening of hydrophilic heads, they can come much closer. So that's what is leading to the increase in size. So there can be more monomers packed into a micelle.
Okay, but maybe the shape also changes, and I leave that to my successor. Thank you very much.
Thank you. Yeah, Professor Velikov, we don't have a lot of time, but please ask your question.
Thank you, Mr. Regan. Dear candidate, first of all, I also would like to compliment you for a very nice thesis. I see that crystallization in crystals can really produce very nice pictures once you use it on your cover. And I'll go straight to my question, or questions which are related to surfactants. In your thesis, you explain how surfactants work in a general way, how they absorb at the fluid-fluid interfaces, having more polar or less or hydrophobic part. And I would like to ask you, because in your system, actually, you have solid-fluid interface, how surfactants actually work in these conditions? Because this is not what has been mentioned in your thesis. So the fluid-fluid interface, surfactants will partition there, part of the molecule will go to the more hydrophobic liquid, the other one in more hydrophilic. However, if you have a solid liquid interface, how a surfactant will be operating?
Highly esteemed opponent, thank you for your kind words and interesting question. So we have done we did some SFG, some frequency generation spectroscopy measurements to explain basically why we were seeing higher supersaturation in the presence of surfactants. So we took into account the interaction between this. solid, and liquid. And we see that there is adsorption. And it depends upon the nature of surfactant.
Thank you.
Time is up. Sorry. And this means that the discussion is closed now, and I request the candidate to read the second part of the formula.
Having thus concluded the defense of my thesis to the best of my ability, and pending the decision of the doctorate committee, I should like to express my sincere thanks to my highly esteemed supervisors, in particular, as well as to those who have so courteously brought forward their criticism, and to all who have honored this ceremony with their presence.
The committee retires for deliberations. Dear candidate, after due consideration of the thesis you have submitted, we have decided to grant you the doctoral degree. Professor Shihazadeh is authorized to confer this dignity upon you in the customary fashion.
I most willingly accept the task assigned to me by the Rector Magnificus of the University. By virtue of the power conferred on us by law and in accordance with the decision of the Rector and the Doctorate Board of the University of Amsterdam, I hereby confer upon you, Mohsen Jahan Qazi, the degree of Doctor and grant you all the rights pertaining thereto by law or custom. In evidence hereof, you will be presented with the degree certificate signed by the rector and the supervisors and confirmed with the Great Seal of the University. Having thus fulfilled the task assigned to me, I have the honor of being the first to address you as a doctor and to congratulate you with the dignity conferred on you. Dear Dr. Qazi, dear Mohsen, here we are. We have finally arrived at this memorable moment in your life and your scientific career. 4 years of work have been successfully completed, and I think you are as proud of the result as I am. A very nice PhD thesis with a wealth of results. I still remember our first Skype interviews, when it was a question whether you would be joining our soft matter group as a PhD student. You were a little hesitant at first because you didn't really know if, as a chemist, you would survive 4 years with physicists. And I think you did, and I think the physicists liked it too, a lot too. Today, it's a pleasure to see how you have developed yourself and improved your different skills during these 4 years. You have been able to show your adaptability and multitasking skills by working on your topic that was not always easy, also because it was very interdisciplinary. You have worked with great dedication on different aspects of crystallization, both from a fundamental point of view as well as on more applied issues. You presented your work at various international conferences and in addition actively participated in our European project related to the preservation of cultural heritage. You ended your PhD with 4 articles already published or under revision and 2 others planned. One of your articles has already been cited more than 20 times since its publication just a year ago, which underlines the interest also other groups have for your work. As no one is perfect, I will also have to discuss the more difficult parts of your 4 years with us. Rather than being the physics part, it was rather the organizational part that posed you a certain number of problems. If I've ever met a messy person, it was you. On organization of experimental data, writing of papers, it all takes a certain degree of organization. I think you learned a lot here over the past 4 years, but not without resisting a bit. For me, as a supervisor, it was a great pleasure to have you as a student and rub shoulders with you for 4 years. Apart from you being hardworking, you always had a good mood and a smile. I would also like to mention your other human qualities that I have deeply appreciated and we will miss in the group with your departure. These are mainly your ability to communicate with transparency, interact with people at all levels with ease, and the most important, your honesty and reliability. I think that in addition, no one of the group will forget your exceptional talents as a chef cook, maybe related to your chemistry side. I will never forget the Christmas dinner at our house during which your lamb curry was finished by the physicists, barely served at the table. In the end, I want to come to one of your surprising qualities that I have noticed in recent months, the calm and serenity with which you submitted your thesis was really amazing. I think in my whole career, this is the first time that I have seen somebody submitting in such a relaxed way. What is the miraculous Indian recipe behind all this? I would really like to have it for future students. Is it the effect of the curry? Then we definitely need the recipe. Otherwise, we really need to learn the miraculous Indian trick behind this. Dear Moshin, I would like to congratulate you once again and wish you a lot of success in the future. I do not know what you will do and how your professional career will shape up, but I hope you preserve what is most exceptional about you, your human qualities. Regard the obtained dignity as an honor and a privilege, and never forget the attendant responsibilities which you now bear towards science and society.
It is a very pleasant duty, most learned scholar, to congratulate you also on behalf of the Doctoral Board of the University of Amsterdam on this newly acquired honor. And hereby I declare this ceremony closed.